Alrighty, looks like the audio is working, so that's always a good thing. Let's see, we have... Yeah. Alrighty, good morning, everybody. We're going to go ahead and get started today, continuing off where we left off yesterday. Where a creature was just borking like crazy. Relax, buddy. We're going to continue the Bork Fest right now. By that I mean, of course, we're going to continue on our figuring out how to quantify levels of solute in your solvent, or in your solution, rather. And so yesterday, we started kind of talking about molarity, right? Which was moles of solute per liter of solvent, solution rather. And so we're going to look at a couple more today. Ones that are somewhat more or less commonly used, at least in chemistry. The first one we're going to see is actually going to be percent by mass. And this is something that you'll see in healthcare, you'll see in biology a lot. They like to use percentages. For some reason, I guess it makes the preparation for the solution a little bit easier calculation-wise. So, when they're making these things up, they're easier to do because it's just by mass. And so what this is going to be, it will be the mass of your solute over the mass of the solution. And since it is a percent, we'll go ahead and just multiply by 100, just to make it nice, right? Notice that the mass of the solution is going to equal the mass of the solvent plus the mass of all the solutes. So whatever stuff you've got going on in there, it's everything's mass. So it's the solvent and all the solutes that you have floating around in your solution. We'll talk about the solution process in a little bit, about how solutions come about, but right now we're just doing basic calculations. So very commonly in healthcare, you'll see 0.9% sodium chloride, right? And that's normal saline. And so this is roughly the concentration of sodium and chloride ions that would be present in your blood plasma or your tissues, or rather the interstitial fluid around those tissues. And so we're going to see that if you continue on in chemistry, you'll see there's something called osmotic pressure, which can really wreck cells or living systems if things are not balanced appropriately. We don't really talk about that in this class, which is okay. But suffice it to say, if you were to, we all know this, right? If you drink very salty water, it dehydrates you. And, if you were to get an injection of pure water, that would also be bad. So you always want some amount of solute particles in your solution if you're going to be injecting someone with it. So that being said, we can go ahead and figure out how many grams of sodium chloride are in 1 kilogram of saline. And for this, we can also just say, just for your own understanding, for water, for dilute solutions like this, typically a liter and a kilogram are going to be the same thing, typically. I will let you know if you're going to need to use the density to convert between them, but for right now, we'll just work with this. So notice it says kilogram of saline, not kilogram of water, or whatever. That's the total mass of the solution. And what you want to do for this sort of formula is make sure that your units are the same. The units need to cancel out. So you see how it just says 0.9%. There's no 0.9 gram percent or something like that. It's just percent. And so in order to make sure that it's a unitless quantity, we have to cancel out our units. So that means that we need to convert that kilogram into grams. So it'll just be 1,000, right? So we know that 0.9%, which is the number we're starting with, will be X grams of sodium chloride in 1,000 grams of solution, times 100%, of course. And of course, thankfully, the reason that this is used is because the math is easy. This comes out to be 9 grams of sodium chloride per liter, essentially. So, hooray. We have done it. This is not one that we use very often in chemistry labs. Just again saying because the calculations that we do typically will involve moles. So we just like to have everything in molars, in molarity, because that will already have moles spelled out for us, makes it easy. So it's all just a matter of, what makes it easiest for your field to use. If it's just preparing the solution, you don't have to actually calculate stuff with it, then, percent might be a good idea. Or, maybe it's not a good idea if you're going to be having to do calculations with it that involve moles. Just more work. So you'll also see this sometimes in some of the old organic chemistry stuff, just because back in the day, they would just do these things by mass and just kind of be like, well, we just threw in this 10% sodium hydroxide. And it's, you'll see that if you take organic chemistry, the chemical equations, as it were, become less important. And so we'll talk about this later in chapter 10, so we'll just leave that for now. So, any questions on that one? We'll do another question with this sort of thing. All right, upping the ante a little bit here. This time I'm asking you how many milliliters of water are in 1 liter of 10% glucose solution. All right, so with that, let's go ahead and let's just say a kilogram. We'll make this a little bit easier. But we can still work with this problem. So with this, that 10% glucose tells us we have, that's going to tell us we have, 100 grams of glucose for 1,000 grams of solution, right? That's what the 10% means. So that 10% of that solution is glucose. So we know in this kilogram, we have 100 grams glucose. This means we have 900 grams of water. Right? They have to add up to 1 kilogram. That's 1,000 grams. So if 100 grams of that is glucose, the rest of the mass must be water. And remember that for water, 1 gram equals 1 milliliter. They're the same thing because the density is 1. So that tells us we have about 900 milliliters of water here in this particular solution. And so if you were to make a percent by mass solution, you would essentially have to subtract your solute mass from the water mass that you're going to need to add to actually dissolve this stuff. All right. Alrighty then, so we have one more, which exists for really kind of one purpose, at least in chemistry. Physics may use it more, but for chemistry at least, the molality of the solution, you know, of course the chemists are not very creative, they're just going to use the same name, change one letter, is also used sometimes. Not as common as molarity by far, but it is still somewhat useful. So this particular concentration measurement is going to be moles of solute like before, but it's going to be over kilograms of solvent. So this is the only one that uses solvent in the denominator. So it doesn't deal with solution as the other ones have. And it's just the mass of the solvent in kilograms. So it must be moles of solute per kilogram of solvent. And we often will use the abbreviation of kind of a fancy little m. Ideally it would be an italic m, but obviously we cannot write in italics. That's a print thing only, so I use a kind of fancy, almost a cursive m. To represent molality. All right, the units, of course, would be moles per kilogram. And it's used for certain physical chemistry calculations. That we'll do a few of those towards the end of the chapter. So we can go ahead and do something. So let's say we have 10 grams of salt is dissolved and 250 ml of water. What is the molality? So just so you know, this unit is even worse. It is called a molal. So it's just absurd, right? We have molar and molal. And if any of you have studied any sort of linguistics or language, L and R are very similar to each other in the ways that our mouths produce them. And in some languages, they actually are interchangeable. Like in Japanese, they don't really use a distinguished L or R, but it's actually kind of a hybrid of the two. But that's a digression, I suppose. But suffice it to say, the chemists are really unimaginative and have made things just difficult by having very similar sounding units. And so now let's actually work on this problem, I suppose. Oops. So in order to find the molality, we need moles and kilograms. So our solute, of course, is going to be the salt, and our solvent will be the water. So we're going to have to convert both of those into the appropriate units. So the solute needs to be in moles, right? So let's start with our mass. If we're going to convert it to moles, we'll use its molar mass. I just happen to have it memorized, but that would be, 22.99 plus 35.45 for sodium and chloride, of course. Sodium and chlorine, rather. Doing this, we get, let's see, 10 divided by 58.44, 0.171. And let's just keep an extra sig fig there. Just remembering that we only have 3, excuse me. And let's use green for the other one. We have 250 mLs of water. And we need this in kilograms, right? However, we know a milliliter and a gram are the same thing. And if we need it in kilograms, we can use the appropriate unit conversion. And we, of course, get 0.250 kilograms there. Hopefully that one is the easier calculation. I should indicate, of course, this was moles. And so the molality of the solution will equal our moles over our kilograms which will equal to, let's do it, we get 0.684, we'll say. You can either leave this as mole per kilogram or just simply squiggly m will work. Either way is fine. So the same with molarity. If you leave it as moles per liter or capital M, doesn't matter. Same thing. So, hooray. So that is our kind of the last one that we're going to talk about in this course. There's a couple others that exist, like percent by volume. Instead of by using the mass percent like we did here, where it was mass of solute over mass of solution, that one would be volume of solute over volume of solution. And so there are just kind of a lot of ways to do this sort of thing. Mole fraction is technically another method of concentration, but that's not commonly used for solutions. So it's just also more work, right? We like to kind of minimize the amount of work we do by using the best units that we can for the task that we're suited for. Alrighty, so with this, let's see kind of how two substances how do things dissolve? And supposedly the easiest way to look at this sort of thing would be to take a look at a molecule like sodium chloride. So let's use, here's our chlorides. Of course, sodium chloride we know is a very nice, orderly crystalline solid. We'll use dark blue for the sodiums. Okay, and so they're, nicely organized like this, right? So there's our happy NaCl. When we take an ionic substance and dissolve it in water, what's going to happen is water molecules around. So let's say that the green is Cl minus in this crystal. What happens is water molecules are going to come around, water molecules being very polar, right, are going to all say, hey, we partially positive hydrogens are really attracted to this negative chloride. Let's pull it off of that crystal. And what you end up having is a whole bunch of water molecules. I'm omitting the lone pairs here, just for clarity. You've got our negative chloride, and we're going to see we have all these lovely interactions happening between the positive, partially positive hydrogens and the negative chlorine ion. And as you can see, depending on how many water molecules are surrounding, I've put 5 here, but oftentimes you'll see 6. And so we're forming 10 different little bonds here. Between the partially positive hydrogen and the fully negative chlorine. This is called an ion dipole interaction. And it is even stronger than hydrogen bonds. So simply because you can see you're going to have quite a few hydrogen bonds happening at once to a fully charged species, and that's going to be a very strong interaction. If you want to look at what happens with the sodium instead, we're going to see that in fact it's going to be the oxygens, which are the negative part of water, right? Which are going to be attracted to that sodium, and they're going to pluck that sodium off and form their own one here. I'm going to try and draw a couple of these waters. Let's do 5 again, why not? I think in reality there are 6, but that's okay. Okay, where that's our sodium, positive sodium, and we can see here all those negative oxygens are going to be attracted to that sodium. And so again, this is going to be an ion dipole interaction. We have an ion, sodium. We have the dipole in water. Those are attracted to each other, and those are going to be what happens when the water dissolved. And we're going to see that in order for a substance to dissolve, the solute-solvent interactions must be stronger than solute-solute interactions. And so, I mean, we know that quite a few things don't dissolve, and there's a number of reasons that things won't. So, for example, if you take chalk, which is calcium carbonate, and you put it in water, it does not dissolve, because the calcium and the carbonate ions are very, very strongly held together. They have very high solute-solute interactions. And so, unfortunately, the water calcium or water carbonate interactions are not strong enough to break that apart. But something like sodium chloride, of course, dissolves very easily because the water and sodium or water and chloride interaction is very strong compared to the sodium and chloride interaction. And so that's really all it comes down to for something to dissolve. And we're going to see here that this can be any sort of interaction. It can be dipole-dipole interaction. It could be London dispersion forces. It doesn't really matter what the type is. In this case, we have ion dipole interactions versus ionic bonds happening. One thing to note is that all of this comes down to a process, or rather a kind of simple rule of thumb, which is that like dissolves like. And we're going to see that things with similar intermolecular forces will dissolve each other because they can continue doing those same intermolecular forces. If you try and take a polar solvent and dissolve a non-polar solute, it's not going to work because you're going to be messing up the happy polar interactions of the solvent molecules. And so you don't want to disrupt that. However, with something like an ionic compound in a polar solvent, we see that we can make very strong new interactions. And so it's kind of that trade-off. Are your interactions before better or worse once you start dissolving? And so that's what kind of molecules will choose, as it were. They'll say, hey, yeah, water, I really like you. Let's go ahead and get together. I'm going to ditch this chlorine. No problem. And sometimes the calcium's like, no, 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 no. I've been with carbonate for 50 years. We're not separating. And so it's that's kind of the battle there. All right, but so we can kind of say that like dissolves like, but in reality, it's all a matter of how strong your interactions are compared to each other. All right, so let's see what happens when we have just a polar molecule. So if we have, say, ethanol, ethanol looks like this. It's two carbons connected together with an OH group on them. We remember that OH groups are polar. We saw that in our worksheet, right? So we do have a polar bit here. So if we kind of just make this into a blob instead, that blob has kind of a polar side and a negative side, and then kind of a neutral side there. But what can happen with this is just like before, is that water molecules can come in. In this case, the negative oxygens are attracted to the positive hydrogen there, or whatever it is in your molecule. And it's the same thing for the other side of things, where we have these hydrogens that are going to be attracted to the negative side of things. So it doesn't have to be ionic for something to dissolve. I mean, we know ethanol dissolves. We know something like glucose dissolves. Glucose looks like this. Where we have all these different OH groups on it. So there's all these little polar bits. And so we end up having water superly attracted, right? Water can just go all over the place here. We have lots of hydroxy groups that can all attract the water. And so we can end up dissolving a glucose molecule like this. And so it's all just kind of a matter of forming nice interactions. And so this is how polar things dissolve. In water, that is. So with ions, you can kind of get them all surrounded by the waters. But for the polar stuff, it's just kind of it's less obvious, as it were, because there's not full charges here. And so these are still just dipole-dipole interactions or hydrogen bonds here. No new interactions. All right. Any questions on that dissolving process? All right. In that case, we have some more vocabulary. And so we're going to talk about kind of states that a solution can be in. We're going to see that we have kind of two major categories of solutions. We're going to see that we can talk about solutions being saturated or unsaturated. Saturated means it has the maximum amount of a solute is dissolved. And you can tell when something is saturated because if you keep trying to add more solute, it's just going to go to the bottom and stay there as a solid. So a saturated solution will have little crystal bits on the bottom. If you're typically, again, we talk about we talk about solutions generally as solids dissolving in liquids because that's what most solutions are. But it's going to be the maximum amount of solute that is dissolved, and any more that you add in is just going to go sit on the bottom, and that's that. There's technically kind of an ongoing process. More is dissolving, but the rest is precipitating out or crystallizing. And so you can see this if you just if you take a little bit of water, add some salt to it, dissolve it, add some more salt to it, dissolve it, add some more salt to it, dissolve it. Eventually, no more salt will be able to dissolve, and any more salt you add is just going to go to the bottom and stay there. It'll start crystallizing on the bottom. And that's how you know you have a saturated solution. An unsaturated solution, on the other hand, will mean it is not yet. It's not saturated. Suffice it to say, using the definition of saturated to explain unsaturated, it means you don't have the maximum amount in there. So you could dissolve more if you wanted to. And so that one is just going to look like a plain old regular solution there. Alrighty, we're going to see that most solids dissolve in water at higher temperatures. We have experienced this in real life. So, say if you're a fan of sweet tea, you want to dissolve your sugar in your tea when it's hot. It's going to dissolve much more quickly, and you'll actually be able to dissolve a lot more in it at a higher temperature, like right after you've boiled it, versus if you let it cool down to room temperature or put ice in it. It's going to take forever for that sugar to dissolve, and you may not even be able to get that much to dissolve, even if it is that cold. So we're going to see that solids typically do dissolve better at higher temperatures. And I'll show you a little graph here of kind of, let me open that. Just so you can kind of see, this is a very common graph pretty much in like every textbook for chemistry. Just so you can kind of have a look at what's happening here. So with this, let's look at a couple of things here. So for most things, as you increase the temperature of the water, you're going to increase the solubility of it. So you can see, for example, potassium nitrate skyrockets over time. You can only dissolve maybe 15 grams at ice temperature, but you put it to almost boiling and you're up past 200 grams. So you can see that's 10 times as much, more than 10 times as much, just by changing the temperature. And of course we know sugar, of course, dissolves a lot better at higher temperatures, so it just skyrockets above even this chart's capacity. Some salts are a little bit more kind of, neutral. Sodium chloride will pretty much dissolve the same at every temperature. Some will go a little bit higher, some go a lot higher. Some, a few, will in fact go down, but that's kind of uncommon. Most solids will dissolve better at high temperatures. And that's something we talk about in 113. But suffice it to say, for us, we just need to understand this trend. So solids dissolve better at high temperature. We're going to see while I'm up here that gases tend to have the opposite. Gases decrease their solubility as temperature increases. And that perhaps you know as well, for if you open a hot can of soda, it's going to explode, right? The trend here is opposite for gases. I'll write this down. But if you have a warm can of soda versus a cold one, if you open the warm one, it's going to, fizz out everywhere, and, it's going to make a huge mess. and all that thing. And perhaps if you've studied any sort of marine biology or anything, cold water can dissolve more oxygen than hot water can, and so you see that a lot of fish organisms or marine organisms really thrive in cold water temperatures, and so that's where like a lot of fishing is done, and just because of the oxygen that could be dissolved there. And so also, if you boil water, as you're heating water up, you see little bubbles forming well below the boiling point of the water. So maybe about 160 Fahrenheit or so, you see those little bubbles forming at the bottom. Those are gases that are just escaping. So you have dissolved nitrogen, dissolved oxygen, other gases dissolved in that water that are escaping instead of water vapor. That's just other gases. So gases, on the other hand, they will dissolve better at lower temperatures. If you think about that, most gases are non-polar. And if you want them to dissolve in water, the more things are moving around, the more kind of unfavorable things are happening. So they're better when they're colder because less unfavorable interactions are happening at colder temperatures. Whereas with solids, the more you move around, the more likely you are to make new happy interactions. And so that's generally why solids dissolve better at higher temperatures. And so with that in mind, there's another classification we have, which is called supersaturated. And that means it was saturated at a higher temperature and allowed to cool slowly. That means it has more than the maximum dissolved. And these are frequently unstable. And for this, we have a lovely video. This is a really cool video. Oh, and of course, it's logged me out. 1 second. Oh, I had it all set up. Okay, so let's go ahead and get this up here. Yeah. Go away. Go away. Okay. Here it is. Okay. This is, as you can see, a liquid. This is a supersaturated solution. I'm going to just illustrate here how you can see my head. There it is. I'm going to just agitate this solution just a little bit. It's unstable. I'm going to throw in just one more crystal into it. And you can see what happens is the entire thing will crystallize. And you can see, in fact, little crystals growing up the side there. And I can go ahead and turn it over. You can see it's fully solid now. While it's not really important, or you can't really tell from this video, it actually heats up quite a bit too. It's releasing a lot of energy because it's unstable. Okay, well, let's look at that again. So, liquid, yes. It is, you can see it bouncing around, kind of. It's an unstable solution. This is sodium acetate. You could buy this online and, find some instructions for how to make it. You can just agitate it a little bit. Sometimes all you have to do is, snap your fingers over this solution and this process will happen. So they're very unstable. Just the slightest, thing can set them off. And as you can see, it completely solidifies. So, cool stuff. This you can buy online, sodium acetate. It's harmless. I wouldn't eat it, of course, but if you do buy it, there are instructions for how to do this. And the fun thing is, you can just heat this up again, and it'll go back into that liquid state until you mess with it again. So you can just keep reusing this. And noting that this process is exothermic, produces a lot of heat, there are actually kind of reusable hand warmers that use this technology. So I wonder if there's a good YouTube video on this. It's pretty cool because they're completely reusable. Let's see. Sodium acetate hand warmer. Okay, let's see. So let's go ahead and look. Yeah, so here, I don't know, this seems pretty reasonable. So, no. Okay, good. So this is what they look like. It's just, you can see like a little plastic bag. It's got a little copper piece in there. And that's going to be what's performing the agitation for this. So who cares? Let's go. So all you have to do is mess with that copper a little bit. And as you can see, you start that crystallization process here, which is going to release a lot of heat. And I hope this person does like a temperature. No, it looks like it's just the same. But I guess they're going to do it again with another one. Here, let's watch it again. So you just press on that, and that is enough agitation to force this to go out. So you can see here it's sodium acetate and purified water, and they put a little bit of a preservative in there as well. And so you can see here there's actually instructions. When it's cold, you just put it in boiling water until it's liquefied again, and then you can reuse it over and over and over again. And so it's rechargeable, doesn't use electricity at all, and that's all it is. So pretty cool stuff. So it's a way of kind of keeping that instability to take advantage of later. Plus it's just cool, right? I mean, who doesn't like seeing things crystallize in like real time? So that's a supersaturated solution. Alrighty, any questions so far on any of these things? We're going to look next at a few kind of special types of solutions. I hope this is the video I'm looking for. Is this? I will find the, maybe it's on this page. We're going to talk about colloids next, but I have to find the video because it's pretty cool. Maybe it's under the last kind of page here. That's osmosis. Whatever, we'll find the other video, I guess, for next time. So with that, there's a couple of other bits of information we can talk about. There's kind of special... Oops. Actually, I should put the quotes in the other one. So special solutions. Oh, they're so cute. I have to take a picture of the dogs. Where's my phone? These are going to be ones that aren't true solutions, as they're not quite homogeneous. They're going to have large particles in them. Oh my gosh, that's so cute. Okay. I'll share it later. Where these ones are going to have bigger particle sizes than we typically will see in regular true solutions. And we're going to see that one of them will be called colloids. Colloids are a special case of solutions. They have very large particles. And these can be proteins. They can be just things kind of just that are big. They form large kind of chunks when they're dissolved. These we're going to see will, as a result of these particles, can displace light. And that's going to be their kind of hallmark feature, is that colloids will reflect light out. If you shine a beam of light through a solution, it just passes through no problem. However, if you pass a beam of light through a colloid, which I will try and find the video of, we're going to see that you'll actually be able to see the beam of light as it goes through. What's cool about this is we can see like lasers and all that through this sort of idea. So if you go to a laser show, they put out a colloid, believe it or not, to make the lasers visible for you. So if you're at a concert or whatever and you can see the lasers, that is a result of a colloid being present. So some common colloids we have. Oh my gosh, I can't spell common colloids. One is smoke or fog. These are common colloids. You have particles of water. Aha, I found the colloid video. That are suspended in air. Or particles of carbon, in case of smoke, that are suspended in air. And you know that, if you try and drive through fog, you can see your headlights as you're going through it, because the particles in that fog are kind of reflecting light in different directions. They're big enough to reflect light. That's the important distinction here. And so we're going to see that you can shine a laser through them as well. So let's look at a video of this. So here we go. I have two mixtures. One of them is a colloid and one of them is not. I'll make it big for us. I'm going to shine a laser through both of them, and we'll see if we can identify which one the colloid is. They look very similar, right? So that one, we shine the laser. We can see the laser as it goes through. Pretty cool. And if we look at the other one, we can only just see it kind of at the bottom where it hits the table. And so this one on the left is a colloid, whereas this one is just a plain old solution. Let's look at that again. So again, here with our colloid, we're going to be able to see the light as it gets scattered by the large particles in this mixture. All right, and doing the same thing on the right again, we do not see the laser through the solution. So try it out. Another one that you have is starchy water. So pasta water would also be a colloid. Often colloids can be a little bit opaque. They are, sometimes they're clear, sometimes they're opaque. Opaque meaning they don't allow light to go through. Milk, for example, is a colloid. It completely reflects the light, just plain old ambient light. That's why we can't see through it. Same with, if fog is really heavy, we can't see through it either. Clouds are another example. Styrofoam. Just kind of foams in general. Gels are colloids as well. So gelatin is a colloid. Foams are colloids. Let's see. So we have a bunch of different types here. Like styrofoam is a gas that is kind of suspended in a solid. You have air kind of suspended in plastic. Little bits. Foams, you have air suspended in liquids. Gels, you have solids suspended in liquids. Clouds, you have liquids suspended in gases. You can have all sorts of different kind of mixtures here. These are all colloids. Another kind of class of these is called suspensions. And they have such large particles that particles will eventually settle out. So if you take do I have a brown color here? Yes. If we take some mud and water, we can mix that together to form muddy water. And we know that it's going to stay that way for a while. Oh my gosh, did I really? Okay, there we go. And it's going to stay that way for a while, right? But eventually, if we just shake it up here and then let it settle out, it'll go back to its original form. Right? You know that, in rivers, sometimes you get churning of the sediment at the bottom of the river. and later on it becomes clear again as it settles out. And so these are called suspensions when you have something like this. So sand in water would be another one. You know, if you can get it, you kind of get that murky color at the top, but eventually that settles out. We see coffee is a suspension as well. Believe it or not, if you leave your coffee long enough, it will settle out to the bottom. You know, depending on how long your coffee has been sitting there, sometimes you'll see at the bottom you have that kind of not quite coffee grounds, but kind of sludgy stuff going on. That's the suspension of coffee. It's just kind of stuff that's settled out a bit. And so these are going to be another kind of special case of solutions. So they're not true solutions in that they're not necessarily homogeneous because they have such large particles, but they will, in suspensions, they will settle out eventually. Blood is another suspension. You have blood cells that are suspended in solution. If you do allow your blood to just stand still, it will separate. Or what's a faster way to do that is to throw it through a centrifuge. So if you ever go to donate blood or something, they will first take a little sample and spin it down just to see how many blood cells you have per, you know, that unit there. It's called a hematocrit. And so they're able to kind of force the heavier things to go to the bottom, and so they can force it to settle out quickly. And so you can use a centrifuge to separate something very quickly. So that's just something that's common. A centrifuge is used, to quickly settle suspensions. So it's just a piece of equipment that you'll see in labs, of course, in you know, healthcare, of course, as well. Centrifuges are kind of used all over the place. So anytime you're needing to quickly get a suspension to settle out, you would use a centrifuge. We see that a lot of chemical reactions that produce solid particles will form suspensions that will eventually settle out as well, but we'll use centrifuges to speed up that process. Alrighty. Still no questions? I do want to put out our solubility rules, but we're going to talk about them on Monday. Alrighty. There are really, for our class, there are only 3 rules to tell us whether a substance is soluble in water or not when we're looking at ionic compounds. And we're going to see that we have kind of 3 things that will tell us if a substance will dissolve or not. So things that will dissolve, let's call them soluble. Any compound with lithium, sodium, potassium, ammonium, acetate, or nitrate is always soluble, no matter what. So we're going to see that any nitrate of any metal will always be soluble. Any polyatomic ion that has sodium as its counter ion will be soluble. Anything that has any of these 6 will always be soluble, no matter what. If we move on to the next one, we're going to see any halide. A halide would be chloride, bromide, or iodide. Halogens, negative halogens. We omit fluoride for this because fluorides are typically not soluble. Is soluble except ones that combine these halides with one of these three elements. So these ones in red, so this tells us that something like silver chloride, silver bromide, silver iodide are all insoluble. They are not going to dissolve. Normally halides do dissolve, but ones of these three metals do not dissolve. So exceptions are going to take place for these next two categories. So same thing with the lead salts. You know, these are also insoluble. But we would expect something like calcium chloride or magnesium iodide to all be soluble. The only halides that are not soluble are ones that are made with silver, mercury 1, or lead 2. All right, and the last one, the last rule we have, we really crunch things down here. Any sulfate is soluble. Sulfate, of course, which is something that includes the sulfate ion. And we have a few exceptions here. Calcium. We have barium, strontium, and then the same ions as before. Oops. So, while we are done for this time, we're going to work with this stuff starting on Monday. We'll do plenty of examples of predicting whether compounds will be soluble in water or not. But I wanted to throw these out here so you can start looking at them over the weekend. So, for example, we're going to see that something like, you know, I want you to be able to look at things like this and be able to predict if they're going to be soluble or not. Apparently calcium is the winner of the day. Apparently I'm using it all over the place. I'll give you the answers for these, but we'll talk about them more next time. And I'm going to just kind of underline the parts that make them soluble. Notice here that we don't have a rule we're going to assume it's insoluble. So everything that is soluble will be covered by these three rules. Everything else is going to be insoluble for us. So we don't have a rule for calcium. We don't have a rule for carbonate. So as a result, we're going to assume it's insoluble. And that's gonna work for us. All right, so we're out of time. We'll continue on Monday. I have put up your gas homework. There's 7 problems that I've written that you'll just do on a separate sheet. There's one gas experiment. We're going to watch a video, take some data from it, and work with that data. And then there's also, I think, a lab sim that's been out for a while that you can work on as well. I'm not going to put your solutions... I could put up your solutions homework, but you may not be able to do it all. And it will not be due this weekend, of course, because we're not done with the chapter yet. So I guess if you're really bored, I can put it up. So, alrighty. Have a good weekend. We'll see you next time.